So I'm going to talk about finding the area between two curves, and I'm going to start with these kind of the easiest ones, the vertically simple polynomials. So remember polynomials and vertically simple, I'll show you what that means when we get our first one. So this is what we're talking about. So example 1, I have two functions, so y equals x is 1, y equals 6 minus x squared is my second one. And then I want to find the area between those two curves on the region between x equals 0 and x equals 1. Okay, so we're going to find the area between those two graphs on this chunk of x's, and we'll use the y-axis also as one of our barriers. So our first thing that we need to do is sketch all of those functions and then figure out where that region is. So step 1, sketch the functions and figure out the region. So I'm only going for the positive x's. Let's see, y equals x, so we get a straight line. 6 minus x squared, and this is just a really rough sketch, right? If you need to make it look nicer, go ahead. I am okay. So this is right, parabola, upside down, up 6. Oh gosh, I guess x equals 0 to 1. There we go. So I'm going to start here at x equals 0, and I will go to x equals 1. So I'm not sure if it's on which side. Well, okay, I do know. So I checked before. It's on the left side of that intersection point. Don't worry, our next example will be one of the other kinds. Okay, so we're going to go between x equals 0, x equals 1, between these two functions and the y-axis. Okay. So this right here, I'm going to do this lightly because I need to come back in just a second. So this little shaded region is what we're looking for. Okay, now we know from fundamental theorem of calculus that area is equal to the integral. So the way we found integrals, like way back, is we would draw rectangles, find the area of the rectangle, and then add up all of those going across. Well, that's just we're going to use this rectangle, so draw a representative rectangle. We're going to use that as a nudge to help us figure out how to write this, this integrand. Okay, so we want to find the area of this rectangle that I just drew. So the area of any rectangle, is height times width. Go back to my green, that orange isn't showing up very well. So the height, this is the one that's kind of confusing. So the height, is going to be the top function minus the bottom function. That's going to give me the height of that rectangle that I have. And this vertically simple, that means that height, the functions stay the same throughout. Notice if I would have gone past this intersection point, then the one on top would have changed. So I would, I'd need to take care of that. But here, in this little region that I've talked about, between x equals 0 and x equals 1, the x squared function is always on top, and the y equals x function is always on bottom. Cool. So the height is going to be the top function, which was the 6 minus x squared, minus the bottom function, which was x. Okay, so that's the height of the representative rectangle. The width, and by the way, doing this little bit, thinking about that area of the rectangle, actually drawing the rectangle, this is going to be so important when we move on to our volumes of revolution. So just get in the habit of drawing those rectangles every single time you're doing areas. Okay, so the width, that is the little short side. So in this case, my short side is a little chunk of x. Right? So think about how you've been doing integrals and a little chunk of x, So sometimes that was a delta x, but we're going to look at the differential dx, because eventually, we're not really going to add up rectangles. We're going to take it and squish it and make it an integral. So what I need to integrate, here we go, area of the rectangle is my integrand. So it is, and I'm going to tidy that up a little bit. How about 6 minus x squared dx. Okay, before I go, I'm going to need my limits of integration. Over what chunk does that dx travel? So I want to add up all of those dx's between x equals 0 and x equals 1. So whatever this part here is, this width, you need to make sure that your limits of integration are also in that variable. Okay, so we're all set up to do it. Well, if you can get this far, then you can get to the answer because, right, that's just nice power rule integration. So integrating 0 to 1, 6 minus x squared dx. So 6x minus x squared over 2 minus x cubed over 3 between 0 and 1. So 6 minus 1/2 minus 1/3 minus, let's see, 0, 0, 0. When I plug the 0 in this time, everything went away, so I can just do a 0. So my answer is going to be 6 minus, I'm pretty sure that's 5/6 if I do negative 1/2 minus 1/3. So here's me being lazy. How about 5 and 1/6 would be the area that's enclosed right here. Okay, so now let's up the ante just a little bit. So example 2, we're still going to stay with those vertically simple polygons. But this time, I'm not going to give you a chunk of the x-axis. We're going to have to do that part. Okay, so the functions look kind of the same. So my linear function is 6 minus x. My quadratic function is just a plain x squared. I'm going to use the y-axis as a boundary. So let's go ahead and do our sketch. So f of x, so that's a line. It's up 6, negative 1 slope. X squared, so that's at the origin opening up. The y-axis, so I'm over here. So the thing I don't know is I don't know where to stop. So here's my region, so shade, right? So I'm looking for this chunk right here, but I don't know where to stop. So I need to find that. So let's find that intersection point, right? So it intersects where f equals g. So go ahead and grab your f, set it equal to g, and solve that equation. So it's quadratic, so that means you need a 0. Move everybody over. I need my x squared is positive. It's the only way I know how to do it. So x plus 3 times x minus 2. So I get 2 solutions. And I want you to think about which one of those we're going to take and why. Sure, right? We'll take the x equals 2. So this point right here, the x value is 2. The y value looks like it would be 4. That negative 3, so I'm going to dot it over here, right? That's that point over there. But I'm not interested. I'm only interested in this chunk over here on the right. And I wasn't actually very specific about that. I should have been more clear. So the y-axis over to the right. Okay, so now I have my area shaded. I know where I'm going to stop, right? So my x interval then is 0 to 2. So now I need to draw that rectangle. Here we go. I'm going to go this way. So then that, remember what that helps me get is the height of that rectangle. So let's write the area of that rectangle. So height times width, or sorry, height times width. So the height is the top minus the bottom. So on top is the x function, I'm sorry, 6 minus x. Minus the bottom is the x squared. So there is my integrand again. And, oh, we're just going between 0 and 2. So I guess that is, I thought I changed up my function. Oh well, that's okay. Change up my function. Why does that look the same? Top minus the bottom. Oh, no, I guess they are different, but oh, well, sure. Okay, they're close enough to being the same. Okay, so 6 minus x squared, or 6 minus x squared. So here we go then. Between minus x squared dx for my width, right? There's my height times the width. So integrate that between 0 and 2. So 6x minus x squared over 2 minus x cubed over 3 between 0 and 2. So 12 minus 4/2 minus 8/3 minus, right, the 0. Again, everybody has an x of that 0. So 12 minus 2 minus 8/3. 10 minus 8 thirds. Okay, I guess I'm doing my ugly algebra now. 30 thirds minus 8 thirds. 22 thirds.